Welcome back, video 2 of 4 for Unit 3. This video is about teaching models what doesn't matter: data augmentation and its 5 families, noise injection in 4 places, semi-supervised learning, multitask learning with hard and soft sharing, parameter tying, the idea that will become Unit 4, and sparse representations. Let's teach some invariances. New bucket data methods. First tool: dataset augmentation, manufacturing more training data from the data you have. The idea: create modified copies of existing examples. 4 images, flip them, resize, crop, shift brightness and contrast. 1 cat photo becomes 20 training examples, and every copy is still, unmistakably, a cat. The label survives the transformation. Free data. A distinction the source makes, worth an exam mark. Augmented data is derived from originals with small changes. Synthetic data is generated from scratch, often by deep networks and GANs without the original dataset. When to reach for augmentation: when overfitting looms, when the training set is small, and generally to improve accuracy. And the deeper reading augmentation is how we teach the model our knowledge of invariances. Orientation shouldn't matter, lighting shouldn't matter. Keep that thought, it returns with the tangent methods at the end of this part. The image augmentation toolbox: 5 families of transformations. Geometric, flip, crop, rotate, stretch, zoom. The workhorses, though stacking too many on one image can hurt performance. Color space shift, the RGB channels, contrast, brightness, simulating different lighting and cameras. Kernel filters, random sharpening or blurring, simulating focus quality. Random erasing, delete a patch of the image. Sounds destructive, but it forces the model to use all the evidence, not one shortcut region. You might notice a family resemblance to drop out on pixels. And mixing, blend multiple images together. Labels, mixing proportionally the boldest family. One warning: augmentation must respect the label. Horizontal flips are fine for cats, and WRONG for digits. A flip 3 is not a 3. Domain awareness first, always. Next data method: deliberate noise injection, and the fascinating result is that noise regularizes. There are 4 places to inject it. Place 1: the inputs. Adding small noise to inputs is augmentation in disguise. In fact, for some models it's mathematically equivalent to a penalty on the weight norms. The model learns to be insensitive to small changes. Smoother, better generalization. Place 2: the hidden units. Even more powerful than shrinking parameters, it forces robust internal representations. This idea matters so much that it became its own famous technique called dropout. Coming shortly. Place 3: the weights, used mainly in recurrent networks. Beautifully, this is a stochastic form of Bayesian inference, treating weights as uncertain distributions. Unit 2's Bayesian statistics, sneaking back in. Place 4: the output labels. Real datasets contain labeling mistakes, and chasing a wrong label at full confidence is harmful. So we soften the target's label, smoothing the unifying picture to write on a shaky train, and your handwriting is rock solid at a desk. A quick but valuable tool: semi-supervised learning, and it lives in this chapter for a reason. The setup from Unit 1's 4 families: a small amount of labeled data, plus a large amount of unlabeled data, trained together. Why bother? Economics. Labels cost time, effort, and money. Unlabeled data is nearly free. The unlabeled mass teaches the model the shape or the input distribution. The few labels then anchor the classes onto that shape. The vivid case: a hospital has 100,000 X-rays, but radiologists, expensive experts, have labeled only 2,000. Semi-supervised training uses all 100,000 to learn what X-rays look like, and the 2,000 labels to name the findings. Why is it regularization? The unlabeled data constrains the representation, reducing variance, cutting overfitting when labels are scarce. And its giant modern descendant, self-supervised pre-training. The GPT recipe is this idea at planetary scale. Architecture bucket now, and first up, multitask learning, MTL. The definition: a SINGLE model trained to perform multiple tasks simultaneously, sharing layers and parameters across tasks. Instead of learning each task separately, the model learns one common representation that benefits all of them. Why does this regularize? Think it through. A feature that helps 3 tasks at once is very unlikely to be memorized noise from any single one. Shared weights receive more total supervision. They're forced toward genuinely general representations. The human analogy from The Source: we learn better studying multiple related subjects than cramming just one. Mathematics helps your physics, physics helps your engineering. Real world: a self-driving car's perception network detects lanes and pedestrians and traffic signs. One shared visual backbone, 3 tasks regularizing each other, and one network to run instead of 3. Architecture on the next slide. The standard MTL architecture, I call it the trunk and branches design. Step 1: the input, say, a camera image, enters the network. Step 2: the shared feature extractor, the trunk. Common layers that learn features useful for every task, edges, shapes, patterns, high-level representations. One shared tutor space in instead of per task learning. Step 3 and beyond: the network splits into branches, the task-specific heads. Each head owns its final layers and produces predictions for its one task. Trunk learns together, heads decide separately. Tesla's perception system famously runs dozens of heads on one shared vision trunk, and BRT-style language models attach different task heads to one pre-trained core. Now, how much should tasks share? That question has 2 answers, hard and soft. Next slide. The 2 sharing regimes: hard versus soft. Parameter sharing. Hard sharing: one physically common set of hidden layers for all tasks, only the output heads are task specific. This is the trunk and branches we just drew. It strongly reduces overfitting, forces a shared representation, and it's the most commonly used form of MTL. SOFT sharing: each task gets its OWN complete network, separate weights, no shared layers at all. Instead, we add a penalty on the distance between the parameter sets, θ1 minus θ2, pulling them toward each other. Knowledge flows through the spring, not through shared wiring. And catch the beautiful connection: that soft sharing penalty is just L2 regularization, aimed at another network's weights instead of at 0. Same mathematics as weight decay, different anchor. Choosing tightly related tasks: hard sharing, cheaper and stronger. Loosely related tasks: soft, to avoid negative transfer. Picture it as one trunk with branches versus 2 towers connected by a spring. A terminology pair that examiners love to probe: parameter sharing versus parameter tying. Parameter sharing is the umbrella idea: use the same parameters across multiple parts or network, or across multiple tasks. Fewer parameters, better generalization. MTLS hard and soft sharing are the flagship examples. Parameter tying is the strict within-network version, literally the same weights, reused in multiple places, enforcing structural symmetry. And the 2 most important examples in all of deep learning convolutional networks: the same filter slides across every region on image, and recurrent networks, the same weights reused at every time step of a sequence. Here's the intuition that makes CNNs feel inevitable: an edge is an edge whether it's top left or bottom right of the photo. Why learn a separate edge detector for every location? Tie the weights: one detector, applied everywhere. Hold this thought, it becomes the entire foundation or unit for. Last architecture tool: sparse representations, the power of mostly zeros. A sparse representation means the model represents data using only a FEW active neurons. Most output exactly 0, a few carry strong values. Look at the example vector: 9 slots, only 2 non-zero. Like a sentence that uses 4 words from a 10,000 word vocabulary. 4 benefits, and they make a tidy exam list. 1 efficient feature learning: 5 strong features beat 100 random ones, noise gets ignored. 2 better generalization: fewer active units, simpler model, less memorization. 3 interpretability: sparse neurons tend to mean something. One fires for edges, another for eyes, another for faces. 4 reduced complexity: mostly zeros means less computation, less memory. Note the altitude shift from the L1 slides. There, we made the weights sparse. Here the activations are sparse. And your brain agrees: recognizing a face lights up a tiny fraction of your neurons, not all 86 billion. ReLU networks inherit this naturally. Every negative pre-activation becomes an exact 0. Quiz 2: the sharing distinction. 2 sentiment analysis tasks, product reviews, and movie reviews should be learned by one system. You give each task its own network, but add a penalty on the distance between their weights, keeping them similar. Which technique is this? A. Hard parameter sharing. B. Soft parameter sharing. C. Parameter tying, as in CNNs. D. Bagging with two models. Picture the architecture: you just built one trunk or two towers with a spring. Pause and answer. The answer is B. Soft parameter sharing. The fingerprint: each task keeps its OWN network and waits, nothing physically shared, and knowledge flows through the similarity penalty, pulling the parameter sets together. Two towers, one spring. Hard sharing: option A would give the tasks one physically common trunk with only the head separate. Parameter tying: option C means literally identical weights reused within a network, like a CNN kernel sliding across an image. And bagging: option D trains independent models on bootstrap samples of the SME task and averages them. There's no cross-task penalty anywhere. Bonus thought: which of these is mathematically the same as weight decay? 7. Soft sharing: L2 regularization, anchored at another network instead of 0. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.